Now in this video we will prove Ito's formula. This is arguably the most important formula in all of stochastic calculus for the Ito integral. It generalizes the fundamental theorem of calculus in standard deterministic calculus, and it's going to give us a concrete way of computing Ito integrals. So the formula is given here in 5.1, but to understand it, let's start by recalling what we did a few videos ago. We computed the integral from 0 to t of bs dbs, right? And we've proved that, well, it's not just bt squared over 2 as your intuition coming from deterministic fundamental theorem of calculus would have you think, but you have to compensate for the fact that the bs process as a non-trivial quadratic variation with this term minus t over 2. Now you could reorganize that formula and tell me that bt squared over 2 is the integral of bs dbs. So this is a certain function of bt, and this is the derivative of that function. But then you have to add to that the term t over 2. Okay, so Ito formula puts that into a far more general context, not just the function x squared, x goes to x squared over 2, but any C2 function. And if you take a f of bt minus f of 0 for f is C2 function, this is going to be equal to the Ito integral of f prime of bs plus a correction term. And this correction term is non-zero, as we will see in the proof, because the Brownian motion has a non-trivial quadratic variation that scales linearly in time. Now, we'll understand that through the proof, but let me first make a few remarks about what this gives us, having Ito formula, and it gives us really a lot. So first of all, notice the following. If you have a function little f in C1, and you take an entire derivative of that function, capital F, that's going to be a function in C2, then applying Ito formula to the function capital F will tell you that the integral of f of bs dbs is capital F of bt. Right? You compute the Ito integral by using an entire derivative, but you have a compensation term which is minus 1/2 of the integral of f prime ds dbs. Now this integral here is not an Ito integral, right? It's just a Riemann integral or a Lebesgue integral, if you want, for every value of the parameter, the probability parameter omega. So this entire thing takes a process and gives you a random variable or even a process as a function of t, and evaluated at the point omega in your probability spaces give you capital F of bt of omega minus the integral times 1/2 0 to t of f prime of bs of omega ds. So this is what's called a piecewise definition for the integral of f of bs dbs. Right? You can fix an omega and compute these things, as opposed to here where the definition that we constructed of the Ito integral involved all of the omegas at once, right? So this is something, if you were thinking of like designing computer approximations for Ito integral, this is something very difficult to manipulate if you go back to the definition, whereas this is something that you can easily simulate using the tools that you have from deterministic calculus, and doing that for every values. Well, you cannot do it for every values in general, but doing that for sufficiently many values of the probability parameter. And this is all sorts of other analytic usefulness. Now, what some people do, of course, if you don't design the entire theory of Ito integration, you could use this formula as a definition, right? If you take Ito's formula for granted, you don't try to prove it, you could say, this is how you integrate in the Ito sense. It's very similar to what you do sometimes when you learn calculus without really doing the mathematics. You could say the definition of the integral of s ds from 0 to t is t squared over 2, because the entire derivative of s goes to s is t squared over 2. But of course, using entire derivative doesn't give you a proper definition, a proper understanding of what the Riemann integral is as a limits of sum It just gives you a way to compute it. And that's similar here, right? If you take that as a definition of the Ito integral, you really don't understand much about what the Ito integral is, but you do have a way to compute Ito integrals by hand. Now, talking about computing Ito integrals by hand, we have example 5.3 just after that tells us how to generalize this formula that we did here for the function s goes to s. Now, more generally, if you have a polynomial, well, you just apply your Ito formula and you get an induction, not even an induction formula, you get a formula that allows you to compute the integral of bs and the bs in terms of integrals of the Brownian. If you've done the exercise and tried to get the formula like this for n equal 2, you would have realized that this is already quite painful. Even n equal 1 was highly non-trivial to compute this from the definition. So this is extremely handy to now be able to do any polynomial with such a neat formula. Now, still a few more remarks before we embark into the proof of Ito formula. The first one is notational. So the way one writes Ito formula, generally speaking, is we write it as the variation df of bt is f prime of bt times the variation of the Brownian plus 1/2 f second of bt times the variation of time. Now, this you have to be careful when you write that. This is what's called a stochastic differential equation, but this d here has no meaning as a derivative, right? Because you cannot differentiate the Brownian. Now, it doesn't have a meaning as a differential form either, and it doesn't have the meaning as a measure, right? dbt is not a measure. The Ito integral is not a particular form of general measure theory or integration against a measure. So these objects don't have a meaning by themselves. This is just a shortened notation for 5.1. So we're really talking about a shortened notation for something that can only be understood in an integrated sense, right? So really, the integral of d of f bs from 0 to t makes sense, as in it is by definition f of bt minus f of b0, which is 0. And the integral 0 to t of f prime bs the bs, this is by definition, well, the Ito integral, right? It's the Ito integral of the process s goes to f prime of bs. Now, on the other hand, the integration of that term makes sense in a classical way of Lebesgue integration, and you could interpret that in various ways, including as a measure. Right, so when we write a formula like Ito formula, which is really an equality of integrals involving both Lebesgue integrals and Ito integrals, we often write it in this condensed form as a differential equation relating the integrants. But this thing called a stochastic differential equation is really not a differential equation, as in nothing is actually differentiated. It's an integral equation. It tells you that the integral of the left-hand side is equal to the integral of the right-hand side, interpreting integrals in the right way. The Ito integral that we've defined is for a function of just a Brownian motion, but we can generalize that and consider the function of time and the Brownian motion. And if you have a function like that of t and bt, the Ito formula becomes 5.2. So what we have here. So what you find is that you have to use, you have two variables, t and bt, and you have to use the gradient of this function of two variables instead of f prime and f second, as you would use if you had a function of one variable. So what I have here, when I write dx and ds, what do I mean by that? Well, my function is a function of t and x. And then I plug the Brownian for the x variable. So when I write dx of ftx, I mean the derivative with respect to the second variable of my function, and then I can plug into that derivative the Brownian instead of x, right? So this is the meaning of this, and with ds, I mean the derivative with respect to the first variable. So what we have, it's written here as a stochastic differential equation, is really here a term that you could also write as gradient of ft_bt dot a vector dt dbt, right? So you would get the derivative with respect to the first variable times dt, that's this term, plus the derivative with respect to the second variable times dbt, that's this term. So in a fundamental theorem of calculus for functions of two variables, this is what you would be integrating. But again, because we're doing stochastic calculus and we have a non-trivial quadratic variation for our Brownian process, then we get this correction term coming from the quadratic variation. And this involves two derivatives in the variable in which we plug the Brownian, which is the second variable of our function t and x goes to f of tx. Now, this is a generalization of theorem 5.1. This is a generalization that's very helpful in practice, but the proof is exactly the same, just a little bit more technical. So we're going to prove it. We're going to prove it to a formula only in the case of a function of the Brownian, but our proof will generalize to functions such as these ones, functions of time of the Brownian, with the exact same proof. Now, one last remark before we embark on, say, proof. What happens if you look at this formula? There's a very interesting case when you're looking at a function f that satisfies a certain partial differential equation. So what happens if dt is exactly equal to minus 1/2 of dx squared of f? If that happens, then what we get, let's use maybe a different color for that, is that this term here will compensate exactly this term there. So what you would get is that in that particular instance, there's no integral against ds in the Ito formula. And what you're getting is that your f of t bt minus f of 0, 0 is equal to the integral from 0 to t of dx of f s bs dbs. Now, if you all know this, dt of f equal minus 1/2 of dx squared of f, second derivative in f, and you know that f of 0, 0 is 0, so you have this PDE, then you can even get rid of this term, and you get that ftbt is the Ito integral of something, of some continuous function of the Brownian. So that almost tells you that f of t bt has to be a martingale. It doesn't quite, because the Ito integral of a continuous function of the Brownian, which is in L2 log generally speaking, doesn't necessarily give you a martingale. It only gives you something called a local martingale. But if you have this condition, right? So what you're integrating happens to be an H2 process, then f of tbt is equal to the Ito integral of an H2 process. And we've shown that any Ito integral of any H2 process has to be a martingale. So this is a very helpful way to check that something is a martingale, some function of time in the Brownian. You give me a function of time in the Brownian, if it happens to satisfy a certain PDE, and its derivative with respect to the second variable gives me an H2 process. So I have this condition, then I can deduce that f of t bt is a martingale. And that's going to be a technique we're going to use to show that a lot of things are martingale. And you might think at first that such a condition is very demanding, but actually it's satisfied by a lot of processes. And when we get to the financial application, this is central to the Black-Scholes model. We're going to get a variation of that PDE called the Black-Scholes PDE. That's our solution to the Black-Scholes SDE has to satisfy. Okay, so as you can see, the Ito formula gives us a lot. It gives us a concrete way of computing Ito integral by hand. It gives us a new way of thinking of the Ito integral in a pathwise manner, so fixing a value of omega and computing integrals for that fixed value of omega. It gives us a way of interpreting stochastic differential equations really as integral equation in appropriate sense. And it generalizes to function not just of the Brownian but of time and the Brownian. It allows us to check whenever such a function defines a martingale, and it's going to be the key technical tool in solving our SDEs. So it's about time we see the proof, and we'll do that in the next video.